Hello everyone, my name is Teja Trivikram. I am from second year Triple B section. Today I am going to present a topic for Caa-2 on the topic of two reaction analysis of salient pole machines in the subject of induction and synchronous machines. So let's enter into the topic. This is the topic name: two reaction analysis of salient pole machines. So let us know about the salient pole. In a salient pole rotor synchronous machine, the air gap is highly non-uniform. So the air gap is non-uniform. The air gap is highly non-uniform in the salient pole rotor synchronous machines. So let us consider a synchronous machines having a two-pole salient pole rotor rotating in anti-clockwise direction within a two-pole stator as shown in the figure number 1. So see the figure number 1. The salient pole rotor rotating in anti-clockwise direction within the two-pole stator. So in figure number 1, the axis shown along the axis of the rotor is known as direct axis or D axis, and the axis perpendicular to the D axis is called quadrature axis or Q axis. It can be seen that the two small air gaps are involved in the path of D axis flux, that is pi d. Thus, the reluctance of the path is minimum. Q axis is represents as pi q. Pi q path has two large air gaps, and it is the path of maximum reluctance. The rotor magnetic field. The rotor magnetic field BR is shown directly vertically upward in figure number 2. This rotor magnetic field induces an EMF in the armature or in stator winding. Simply, armature is also known as the stator winding. So, if a lagging power factor load is connected to the alternator, an armature current IA will flow. The armature current IA lags behind the excitation voltage by an angle psi. See the figure number 2. The armature current IA produces the stator MMF, which lags behind behind the armature current by the 90 degrees. The stator MMF produces the stator magnetic field along the direction of MMF. According to Blodel's two reaction theory, the stator MMF can be driven into two components wise: the direction axis component and the quadratic axis component. So let's see some brief equations. If phi d is equals to direct axis flux and phi q is quadrature axis flux, and SD is reluctance of direct axis flux path, SQ is reluctance of quadrature axis flux path, then direction axis flux, that is phi d is equals to FD into SD. Consider this is as equation 1, and quadrature axis flux phi q is equals to FQ into SQ, and consider this is as equation 2. Since SD is less than SQ, the direction axis component of stator MMF produces more flux than the quadrature axis component FQ of the stator MMF. The direct axis and quadrature axis components of the stator fluxes produces voltage in the stator winding by armature reaction. So let EAD is equals to direct axis component of armature reaction voltage, and EAQ is equals to quadrature axis component of armature reaction voltage. Since each armature reaction voltage is directly proportional to respective armature current and lags behind the armature current by 90 degrees, the armature reaction voltages can be written as EAD is equals to minus JL dxAD, and consider this is as equation 3, and the equation 4 is written as EAQ is equals to minus JLQ into XAQ. So these two are the equation 3 and equation 4, where XAD is the armature reactance in the direct axis per phase. XAQ is the armature reactance in the quadrature axis per phase. Here XAQ is less than XAD because the EMF induced by the given MMF acting on the direct axis is smaller than the EMF on the quadrature axis due to its high reluctance. Now the resultant EMF induced in the machine is ER is equals to EF plus EAD plus EAQ, and the fifth equation is ER is equals to EF minus JLD XAD minus JLQ into XAQ. So this is the fifth equation. Also the resultant voltage, that is known as ER, is equals to the phasor sum of terminal voltage and the voltage drops in the resistance and leakage reactance of the minimum armature. Thus the sixth equation is given as ER is equals to V plus IA into RA plus JLA into XL. This is the sixth equation. Then coming to the armature current, the armature current is split into two components. One is phase with the excitation voltage, that is represented as EF, and the other in phase quadrature to it. If IQ is equals to quadrature axis component of IA in phase with EF, then ID is direct axis component of armature current lagging EF by 90 degrees. Then the total armature current is the phasor sum of IQ and ID. That is IA is equals to IQ plus ID, and this is the seventh equation. Now from the equations of 5 and 6 we get EF is equals to V plus IA into RA plus JLA into XL plus JLD into XAD plus JLQ into XAQ. This is the equation 8 from equation 5 and 6. And from equation 7 and 8 we get EF is equals to V plus IQ plus ID into RA plus J into IQ plus ID into JL plus JLD into XAD plus JLQ into XAQ. That is EF is equals to V plus IQ plus ID into RA plus JLD into XL plus XAD plus JLQ into XL plus XAQ. And the final ninth equation is EF is equals to V plus IQ plus ID into RA plus JLD into XD plus JLQ into XQ. So this is the equation. This is the ninth equation of the. So coming to the final equation, where XD is equal to XL plus XAD and XQ is equals to XL plus XAQ. The reactance XD is known as the direct axis synchronous reactance, and the reactance XQ is called as the quadrature axis synchronous reactance. So therefore the final 10th equation is written as EF is equals to V plus IA into RA plus JLD into XD plus JLQ into XQ. Equation 10 is the final form of the voltage equation for the salient pole synchronous generator. So this is the final equation for the salient pole synchronous generator. So this equation belongs to the synchronous generator of the salient pole. So thank you one and all.